Let us look at functions and relations. The same functions that we have been doing for the last around 75 sessions. Given two sets A and B, let's say A is the set containing -3, -2, -1, 0, 1, 2, 3. And B is equal to the set containing 0, 1, 4, 9. Now, is it possible to figure out whether there is any correspondence between the elements of set A and set B? Now, if we look at it, notice that if we take any element in A and square it, we get a value which is present in the set B. This can be represented in the following way. We can say M is a set of ordered pairs -3, its square is 9, -2, 4, -1, 1, 0, 1, 1, 1, 2, 4, 3, 9. Or in the set builder notation, we can write it as M is equal to the set of ordered pair x, x square, where x is in A and x square is in B. Note that A has 7 elements and B has 4 elements. Therefore, A times B, that is the Cartesian product of A and B, has 28 ordered pairs. So we can explicitly write out the Cartesian product. Just follow it like this. -3, 0. -3, 1, -3, 4, -3, 9, -2, 0, -2, 1, -2, 4, -2, 9, and so on. Now, M is a subset of A times B. That is a specific subset of A times B. In general, a relation from A to B is any subset of A times B. We can also say every subset of A times B is a relation from A to B. So here M is a relation between A and B. The set A times B is called the Cartesian product of A and B and is defined as A times B is equal to the set of ordered pairs A and B, where A is in A and B is in B. We saw this definition in the previous session also. Here, x square is the function which relates an element x in A to an element of B. So the way we write it is f colon A relates to B, where f of x is equal to x square. A function f from A to B is a relation satisfying the following property. And what's that property? For all A in A, there exists a unique B in the set B, where the ordered pair A comma B is in F, where F is a subset of A times B. Now, a relation between two sets is simply a subset of their Cartesian product. In a relation R, each element of A is related to 0 or more elements in B. So, R is a subset of A times B. In a function, each element of A is related to exactly one element of B. In case of a relation, 0 or more elements. In case of a function, exactly one element of B. So we have for all A in A, there exists a unique B in B such that the ordered pair A comma B is in F and F is a subset of A times B. The same two sets A and B can have many different relations between them. Each relation is represented by a different subset of the Cartesian product of A and B. Now, a simple example. Imagine a mirror F. Each person standing in front of the mirror represents an element of set P. The mirror shows an image, that is a reflection. an element of set I. For every person standing in front of the mirror, there is exactly one image formed. Thus, for every P in P, there exists a unique I in I such that f of P is equal to I. Now let us extend the analogy. Suppose two or more different people may produce identical images in a mirror. This illustrates that the different elements of P may have the same image I. This corresponds to P1 is not equal to P2. That means different people. But f of P1 is equal to f of P2. Now, if you want to impress everybody, look at this, but read it in normal language. So you would read it as for all A in the set A, there exists a unique B in the set B such that the ordered pair A, B is in F and F is a subset of the Cartesian product of A and P. But of course, it will be great if you understand it while reading it. So that was functions and relations. That's it for now. Bye.